This is hands-on on how to calculate the density of state for any material of interest. So the first thing we are going to do is we are going to first download the material of interest, the correct structure for the material. So we need to know the actual space rule of the material. So in our own case, our material of interest is silicon. So we go to the materials project website or any other website that provides crystal structure of materials. So here we are. We download silicon. Then this is the FD3 bar M crystal structure for silicon, which is the FCC structure for silicon. So it's more advisable again when we are downloading. It's most advisable to check this E above all. Mostly if it is zero, it means the material is stable. And sometimes this flag at times indicate that an there is something, an issue with the SCI file we want to download that we need to read and take into consideration. So we can check anyone with flag and see what they wrote there, that like gap value is approximate and using a loose key points mesh. So for stable materials, we need materials that they have E above all approximately equals to zero. That is very low, not high. So now this is our FD3 bar M. So we click on it. Here we are. Then we can click on the CI file, and then we want the primitive cell. So here we have, we download the silicon primitive cell. So now I can visualize the structure I downloaded using any visualization tool that we have. Vesta, Ovito, uh, anyone that we have, we can use it to visualize the structure. So now you can open the structure you downloaded either by dragging it to Burai, or you can open it directly from Burai also, if you know actually where the folder you downloaded it, if you can locate it on Burai. So I think for your users, I think Dell, and I can find it on downloads. Should be able to find it here in downloads. So let's scroll down. Yeah, and here we are. This is the silicon primitive cell that that was downloaded. So you can open it if you want to open. So, but in order to make sure that it is the one I downloaded, because I have many files here, so let me redrag into Burai. Okay. So now you can edit your file as as much as you like, the way you like, to suit what you want to use it for. So you click here on the SCF. So you can adjust the SCF, the parameters you want to adjust in the SCF using this section. So you can, if I want to set the threshold to -8, -10 to be more strict, I can change it here. The electron maximum step, you can adjust it here. So you can do many things here actually. From the Burai, you can do your editing here. If you want to add magnetization to the material, you can add magnetization to it. So you can do many things here. This is if you want to do GGA plus U by adding the Hubbard parameter. So we have many things we can do from Burai also, but you need to click the appropriate section you want to edit. If you click on geometry, you cannot do much on the material other than just, you can only edit the lattice parameter, the element. Maybe if you want to add dopant, you can add dopants to it here. From here, you can add dopants to the material. So you just click on add on if you want to add dopant to it. So you have less function you can do with geometry. So each tab has its own function it is going to do. So you can click on it. If I want to change the VC relax and the relax, I click on optimize. So if I want to edit the band gap section, I can, the density of state section, I can also change my K-mesh from here. So you can do many things right from here, from Burai. And if you want to edit manually too, is good. So the next thing is just to save your file. You can use save as, you can use save depending on what you have. So if I say, let me say I want to use save as, so let me just assume I want to save here and save maybe silicon diamond crystal structure, and maybe I can use primitive, though I have one already, so I can just do like this, and this file has been saved. So now we go to the main task of calculating the density of state for our material. So the first thing is I have to locate the file which I just downloaded now. Okay, here. So this is the one I've already edit according to what I want. So we discussed in the class that we need to always add this section, this output. In addition to what has been taught before, we need to add this output directory section. That is to be temporary because we want our folder to be as clean as possible, as neat as possible. So we'll be able to follow up with our calculation and avoid confusion. So let's assume this is my SCF file. This section, I use SCF as my section. I define my this section as SCF because that is the calculation I'm interested in. So the next thing is you do editing of what you want to edit, and if you want to optimize some parameter, you can optimize the parameter in which you want to optimize. Actually, this, let's say for learning purpose, we start with something around 25 because this is 100 here. So your E cut and your E cut row, there is a relationship at least it should be E cut row should be 4 times greater than your cutoff energy. That is, the charge cutoff density must be 4 times greater than your cutoff energy at least. So some specified times 8 times by times 12 greater than 8, but the rule, the minimum should be, it should be 4 times greater than your EPOT. So now I have edited the file according to what I need. So let's assume I want to optimize my system first. We just pick some sections and do. So the first thing is I locate my file on Burai. So you can use ls as explained before. So I know I have it on MNT, then followed by C, followed by users, and I think Dell. And in Dell, this happens because I have space. I didn't name the file properly in a way Ubuntu can read because there is space. I should have used an underscore. It would be more appropriate for Burai to read. But that is by the way. So here we are. I have to put silicon because I have many silicon, diamond, primitive with the same name. If I use the tab, it gives me two options to choose. So this is the one I want to use. So I can still do ls to check my folder. And now let me enter my cd optimization file. Okay, so the first thing is to ensure that you don't encounter the pseudo potential error, just save your pseudo potential in the same folder as the file you are running as for beginning, but you can save it in any folder. Just if you can locate the directory of the folder and specify it to Quantum Espresso. So, and as to avoid error in the pseudo potential, you can just click Control A, then copy the name of the pseudo potential, like you as if you want to rename it. Then you paste it here. So to ensure that you are on the same page uh, with uh, with the pseudo potential you specify. So now let's run our file. We have pw.x. Silicon save.in and then silicon.scf 2.out, because in my density of state file I have sections where I have one, so let's use two so we can be on the same page. So it's running and we can confirm if we have what we need. So let's check among our output file. We should be able to find silicon scf2 now as an output file. And here we are. This is it. We have any output file with silicon scf.2. Okay. So we have a new file with our output file here. So we just finished the SCF part, and mostly we don't need any information from this. What we need now is relax. In the relax section, what you just have to do is specify to the calculation that you want to do relax now, and you can specify the first convergence threshold. But for now, we don't take much about these sections. What we need most is this calculation, our studio directory, and our output directory. So we still specify the same TMP because it has to match with the one in our SCF, because sometimes you need some information for the SCF from the SCF to run the relax. So mostly it's better to specify the same folder. Okay. So now we had this section, our calculation relax. Then in relax, we need to add a section in order to be able to for the system to perform the relax. Here is it. We have ion dynamics to we had this section ion dynamics to be BFGS. This so this cell we are coming when we come to VC relax, we are going to add this section, but for now there is no need for this section. So because you choose 100 for the SCF, let me also do this, though this is what we are going to optimize later. But actually before coming to relax, you should have optimized your system from here. You should optimize your pseudo potential. You should optimize your you should have optimized your key points parameters by fixing this cutoff energy and then varying this from 222. You can go in a step of 111, 222, 333, 444 until you start visualizing that you have convergence. So for me, I already did it. I fixed it and I have my result here for the cutoff energy convergence, and So these are the convergence I already did. So this is the for the K point. So here we can see we start having the minimum around 444, but because using 666 does not cost much computational, does not consume much computational resources too. So I decided to go to 666. And then if we come to the theory, we are going to see realize why sometimes we prefer to choose the even cutoff K point. And this is for the cutoff, this energy here we have. So in this one, in order to convert your cutoff energy, so you fixed the K point, you choose your K points to be fixed, and then you vary the cutoff energy. So, and this is what actually happens here. While in this file, I have 200 before, because when I did the convergence for the cutoff, I have it to be, for the cutoff energy, I have it to be something around 40. So I chose 40. So I chose 40, and here I can use 200, or you can start from 160. From 160 above, everything is okay. So the rule is just you need times 4 of it, and this is my already converged cutoff that I already inserted into this file. Then we can run our relax calculation also by using pw.x silicon dot relax.in, and then we save it as, so here we have it running, and we have our output file here, silicon.relax. So we have the relax. So what do we mostly need in from the relax? We need the final atomic position here. We copy it. When you copy this new atomic position, and you put it in your VC relax file. So when you prepare a VC relax file, you take the atomic position from your relaxed calculation and put it in the what? In the VC relax, so that the system can start from a well converged atomic position. So it doesn't have to do much work in relaxing, because VC relax have to perform some relaxation before actually doing the VC relax. So there is relaxation in VC relax, but sometimes just if you want to give this, let the system start from an ideal atomic position, you can first run your relax, and then you take the atomic position from relax to this. So it will start from an approximately converged atomic position for the VC relax. So you take it, and then you add this section, cell dynamics, which is BFDS, and then you put the pressure convergence threshold you want. So this is the section you are going to add in your VC relax. One, you put the atomic position you get from relax calculation into the atomic position for the VC relax, and then you add this section, and then from here you have to specify to the system that you want what? VC relax. And you can see the cutoff energy has been fixed to 400 and 200 after convergence, and then the K point too also. So now you can run the VC relax. So here we have an output file. So this is just a normal error. The following floating point is, sometimes it's normal to have those error in Quantum Espresso output file. So that is This is our VC relax. So what do we need from the VC relax? This is where you get your optimized lattice parameter. So how do we do it? What you do is you check where it gives you the cell parameters here. Make sure the cell parameters you are using is the one that is attached to the end final coordinate, because you can have some other cell parameters upward also. So you can see this is another cell parameters, but the system has not tell us that this is the what end final coordinate. So make sure you are using the cell parameters that is attached to what? To the end final coordinate. So you search for end final coordinates. You can use Control F and search end. So this is not what we want. So we keep end of self-consistent, end of VFGS. Yeah, we got our end final coordinate. So mostly this is the one you are going to use. And what do we do here? You take this A lat and multiply by what? A11. So you copy it, you copy something like this. A lat, like we have here. Then multiply by what? This A11, since it's a cubic. For non-cubic, you still have to do you do some multiplication also. You have to do some multiplication, but since our system is cubic, we pick it and then we multiply it by okay. Then we multiply it by this A11. You copy it and then you can do the multiplication. Anything it gives you, mostly this comes in bar. It comes in bar, and then you can convert your bar. So you can use bar to angstrom. So you can use the converter here to take the value you have to bar. So this is our optimized lattice parameter. Control C. So assuming we are using the conventional cell, this is what you will do. So let's assume, so I put it here in angstrom. Okay. So I have this here in angstrom, but because we have a primitive cell, so I don't have to do this adjustment. I just use the one in the board directly, because we can see when I decided to adjust it to 2.7 to 2.7, when I decided to adjust the lattice parameter to 2.7, so we can see, so this is what I got in angstrom. So we can see how the system is. So it's not ideal like this. The first one like this, it's more ideal. So, but if you are using the conventional cell, you actually need to do that calculation and take this your new lattice parameter you got this this one in angstrom preferably to your new SCF file, and that is why you have to have a new SCF file. So I have 5.4 before, but now I am using 5.16 I got from here as my new relaxed atomic position. So what you do, you create a new SCF file, which here I named that SCF1. So you create a new with the with your lattice parameter. So this is it, the 2.735 I got in angstrom, but it's from viewing the structure, I view it more ideal to use that of that 5 points something angstrom because it shows it's more ideal than that the one that was compressed when I converted to angstrom. But this is ideally what you should do. Then now you create a new SCF file with your converged lattice parameter, with your converged atomic cutoff charge. Then the cutoff charge density is derived from by multiplying the cutoff and cutoff charge by some values, and then you have your converged lattice parameter K points, your converged cutoff, your converged new atomic position, because you have to copy the new lattice atomic position that you got from relax to this new SCF file also. So everything now here is converged. Then you can run another SCF calculation. You can run another SCF calculation. So in order to get the converged, to make your system to be converged. So this is if we need to calculate something like the surface energy, we will need energy of the what of the bulk material. Or when you were told to compare some which metal is stable, and we say that the first thing is you ensure that what the value you are giving are well optimized. So now you can run a well optimized self-consistent calculation to get your what total energy from the what optimized system. So this is SCF one, and I can name it SCF one also. Let me write it in the file. So yeah, so the output file we will get from here now, we are going to have that our total energy here is for the what optimized system. So in order to keep the video short, I will first save this one for the optimization process.